It's the most asked system design question on Earth, and it looks like a joke. Turn a long URL into a short one. That's it. You could build a working version in a weekend with a hash map and 40 lines of code. So why does it show up in staff-level interviews at Google and Amazon? Because make it work, and make it work for 100 billion links at 100,000 redirects a second, are completely different questions, and the interviewer is watching which one you answer. The whole design collapses to two decisions that sound trivial and aren't. First, how do you generate the short code? And the senior answer is a counter, not a hash, because it makes collisions impossible instead of merely unlikely. Second, when someone clicks the short link, which HTTP redirect do you return? And if you pick the obvious one, you just silently threw away every analytic your product team asked for. Get those two right, and everything else is plumbing. Get them wrong, and no amount of caching saves you. Functional, and keep it tight. Given a long URL, produce a short unique alias. Given the short alias, redirect to the original. Two operations. Then the ones that separate senior candidates. Custom aliases. Can a user request /mybrand? Expiration. Do links have a TTL or live forever? Analytics. Does the product need click counts, geography, referrers? Say clearly what's out of scope. User accounts, editing, so you don't sprawl. Non-functional is where this system actually lives. It is overwhelmingly red-heavy. The redirects outnumber the shortenings by around 100 to 1, and that single fact drives every storage and caching decision. Latency. A redirect is on the critical path of a human clicking a link, so it must be fast, low tens of milliseconds. Availability over consistency. If the shortener is down, every link everywhere is dead, so high availability is non-negotiable. And a brand new link being readable a second late is completely fine. And the codes must be short and hard to guess. Name those, and you've framed the whole problem. Do the math out loud because it sizes two things, the key length and the storage. Say 100 million new URLs a day. At 100 to 1 read-to-write ratio, that's 10 billion redirects a day. Roughly 115,000 reads a second. Call it a couple 100,000 at peak. So, heavy reads, modest writes. Remember that. Now the key length, which is the fun part. Will encode in base 62, 26 lowercase, 26 uppercase, 10 digits. How long must the code be? 62 to the power 6 is about 56 billion. 62 to the 7 is about 3.5 trillion. At 100 million new URLs a day, a 6-character code exhausts in under 2 years, but 7 characters lasts over 80 years. So 7 base 62 characters it is. That's the answer to how short can it be. Storage, 100 million a day, times 365, times 10 years, is on the order of 300 billion links. At roughly 500 bytes each, the code, the long URL, some metadata, that's around 150 terabytes. Big, but it's just key value data. Two numbers, the key length and the footprint, and each one just made a design decision for you. Here's the heart of the whole problem, and where most candidates go wrong. You have 3 ways to generate that 7-character code. Option 1, hashing. Take the long URL, run MD5 or SHA, and keep the first 7 base 62 characters. Sounds clean. But 2 different URLs can hash to the same code, a collision, and the more links you store, the likelier it gets. So before every write, you must check if that code already exists, and if it does, rehash or append and try again. That's an extra read, sometimes several, on every single write. Option 2, the counter. Keep a single global number that only ever goes up, and for each new URL, take the next value and base 62 encode it. Counter equals 1 gives you a 1-character code. Counter equals a billion gives you a 6-character code. The magic? Because the counter is always unique, the code is always unique. Collisions are mathematically impossible, so you never do a collision check, and writes are a single operation. That's why the counter is the senior answer. It turns probably unique, verify every time, into unique by construction. Option 3, pre-generated key pools. A separate service generates unique keys offline into a database, and your app just hands them out. It dodges collisions too, at the cost of running and securing that key service. The counter is the cleanest story to tell. So now, let's break it, because a naive counter has two serious problems. A single global counter has two problems, and naming both is the staff signal. Problem 1, it's a single point of failure and a write bottleneck. Every shorten in the entire system has to increment the same number, one row, one hotspot, and it caps your write throughput and dies if that node dies. The fix is range-based allocation. A central coordinator hands out ranges of the counter. Server A gets 1 to 1 million, server B gets 1 million to 2 million, and so on. Now each app server burns through its own range locally, in memory, with zero coordination per write, and only comes back to the coordinator, rarely when its block runs out. You've turned a per-write global lock into a per-million write one. Something like Zookeeper or a database with atomic range increments plays the coordinator. This is the same idea as Flickr's ticket servers and Twitter's Snowflake. Problem 2. A plain counter is sequential and therefore enumerable. Code 5 is followed by code 6, so anyone can walk your entire linked database and scrape every URL, a real security and competitive leak. The fix is to keep the guaranteed unique integer, but make the output unpredictable. Run the counter through a reversible bijective scramble. Multiply by a large prime and modulo or a small Feistel permutation before base 62 encoding. Unique by construction, unguessable in output. That combination, ranges for scale, a bijection for unpredictability, is the answer that lands. Now, the decision nobody expects to be a decision, and it's a favorite senior curveball. Someone clicks your short link. Your server looks up the long URL and sends back an HTTP redirect. But which one, 301 or 302? A 301 is a permanent redirect. The browser and every proxy in between are told this mapping never changes, so they cache it. And the very next time that user clicks the link, they jump straight to the destination without ever hitting your server. That sounds like a gift. Free load reduction. Until you realize what you just lost. You can no longer count that click. Your analytics, total clicks, geography, referrer, the entire product feature go dark because most clicks never reach you. A 302 is a temporary redirect. Nothing caches it, so every click comes back through your server, you log it, and then redirect. You pay for the extra round trip, but you keep your analytics and you keep control. You can change the destination, disable an abusive link, or rate limit it anytime. So the answer is a genuine trade-off. You must say out loud 302 by default, because for most shorteners, the click data is the product. Choose 301 only if you truly don't care about per-click analytics and you want to shed load. Knowing why the status code changes, who counts the click, is one of the highest signal things you can say in this entire interview. The data model is almost insultingly simple, and saying that confidently is itself a signal. Don't over-engineer it. It's a key-value lookup. The short code is the key. The long URL is the value, plus a little metadata. Creation time, owner, expiry. There are no joins, no complex queries, no relationships. So at 300 billion rows, you reach for a store built for massive key-value scale and horizontal sharding, a Cassandra or a DynamoDB, sharded by the short code itself, which distributes reads and writes evenly with no hot partitions. Could you use SQL? For smaller scale, absolutely, sharded by code. But at hundreds of billions of rows, a wide column key-value store fits the access pattern better. Now the read path, which is what actually gets hammered a couple 100,000 times a second. It's read-heavy with a small, hot working set. A tiny fraction of links, the viral ones, drive most of the traffic, which is the textbook case for caching. Put an in-memory cache, Redis, in front of the database holding the hottest code to URL mappings with LRU eviction. A cache hit, the overwhelming majority, is a memory lookup and an instant redirect. A cache miss goes to the database, then populates the cache. And because a redirect for a given code is identical for everyone, you can push it all the way to a CDN at the edge, geographically close to users. Cache aggressively because the data barely changes. That's the whole read path story. Let's make it concrete. Trace both paths, then break every stage. Write path, shorten a URL. The request hits an app server that already holds a local range of counter values. It takes the next integer, runs it through the bijective scramble, base 62 encodes it to 7 characters, writes the code to URL row to the database, and returns the short link. Break it. The app server crashes with unused counter values in its range. Those integers are simply lost, we skip them, and there are trillions, so who cares? We never reuse or block. Break it again. The coordinator that hands out ranges is down. Servers keep serving from their current range and only stall on new range requests, so you make ranges large and the coordinator's blip is invisible. Read path. Expand a code. The request hits the CDN or cache first. On a hit, instant 302. Break it. Cache miss. Fall through to the database. Redirect. Backfill the cache. Slightly slower, not an error. Break it again. The code doesn't exist at all. Return a clean 404. Don't hang. Break it a third way. A link is expired. The row's still there, but on read, you check the TTL and return 410 gone instead of redirecting. Every stage either succeeds fast or degrades cleanly. And walking an interviewer through these failures, unprompted, is exactly what staff level looks like. Let's handle the features that ride on top, starting with the one the 302 bought us. Analytics. When a click comes through, you must log it. But you must not make the user wait for that logging. So you fire the redirect first and record the click asynchronously. Drop an event onto a queue like Kafka and return the 302 immediately. A downstream consumer aggregates clicks, geography, and referrers into an analytics store completely off the hot path. The redirect stays fast. The data still gets counted. Custom aliases. A user wants /launch. Simplest model. Treat it as a user-supplied key. Check if it's taken, and if free, write it straight into the same table, bypassing the counter entirely. Expiration. Store a TTL. A background job lazily reclaims expired rows, or you let the key value store's own TTL evict them, and reads check expiry as we saw. Rate limiting and abuse. Shorteners are catnip for spam and phishing, so you rate limit creation per user or IP, and run destination URLs against a safe browsing block list so you're not redirecting people to malware. None of these change the core. They hang cleanly off it, which is exactly the point of a design with a clean core. The follow-ups that show range. Counter versus hash. One more time. If pushed, say it crisply, hashing needs a collision check, a read on every write. The counter is unique by construction. 0 checks, that's why it scales writes better. Global and multi-region give each region its own counter range or a region prefix in the ID, so no cross-region coordination is needed on the right path. Replicate the key value store asynchronously, since a stale by a second link is fine. Idempotent shortening. Should the same long URL always return the same code? Only if you add a reverse lookup, URL to code, which costs an extra index, often not worth it, and you just accept duplicate codes for the same URL. The hot link, the thundering herd. A link goes viral. It's cached everywhere by definition, so it's actually the easy case. The CDN and Redis absorb it. Bots and inflated analytics filter bot traffic in the async pipeline, not on the hot path. And security, never blindly redirect. The open redirect and phishing risk is real, which is why 302 plus a block list plus the ability to disable a link matters. Each of these is a one-liner that shows range. The red flags, the traps that sink candidates. 1. Defaulting to hashing without ever mentioning the collision check. Fix it with a counter, unique by construction. 2. A single global counter with no scaling story. Fix it with range allocation. Ticket servers, Snowflake. 3. Sequential, enumerable codes that let anyone scrape your database. Fix it with a bijective scramble before encoding. 4. Returning a 301 and then promising analytics. Those contradict. The 302 keeps clicks on your server. 5. Over-engineering the database with joins and relations. It's a key-value lookup. Use a key-value store. 6. Forgetting the read-to-write skew. It's about 100-to-1 read-heavy, so the cache and CDN are the design, not an afterthought. 7. Logging clicks synchronously on the redirect. Make it async via a queue. Redirect first. 8. No cache and no CDN for a read-dominated system. The hot working set is made for caching. 9. Ignoring custom aliases, TTL, and abuse. They hang cleanly off a clean core. And 10. Blindly redirecting to any URL, a block list and rate limits, or you're a spam and malware vector. So, a URL shortener is a read-heavy key-value lookup, and you win it on 2 decisions. Generate the code with a counter, not a hash, so uniqueness is by construction and writes need no collision check. Then scale that counter with range allocation and make it unguessable with a bijection. And return a 302, not a 301, because for most shorteners, the click data is the product. Everything else follows cleanly. A key-value store sharded by code, a Redis cache, and a CDN for the 100-to-1 read skew, async analytics off the hot path, and custom aliases, TTL, and abuse controls hanging off a deliberately simple core. That's the difference between the weekend hack and the 100 billion link system. Same idea, completely different engineering. Master this one, and you've got the vocabulary, counters, base 62, caching, redirects, that shows up in half the other interviews too. Practice this exact interview with an AI interviewer that pushes back, free at crackit.io. Design the system, then go defend it. See you in the next one.